in the last video, I showed you why the substitution method works. It's basically the inverse of chain rule differentiation. So in this video, we're going to actually do some examples using the substitution method. So when we have some expression that might be a composition, and we see in that integrand as well, the derivative of something, like when we are looking at it and we see both of those pieces in there, this is where we can use the substitution method. We're going to let u represent that interior function g of x. Okay, so what this says here is that du equals du dx times dx, and that cancels out, equals g prime of x. So we're going to then let g prime of x represent the derivative of u. So we're going to perform this substitution or determine how to choose u, and then we will integrate with respect to u. So basically we're going to take all of the x's and turn them into some sort of u. So, once we have everything in terms of u, then we can integrate it, and that u substitution makes it look simpler. So after we integrate, we just want to make sure we remember that we turn everything back into x. So we want to put the x back in there because we started with x, we want to end with x. We're just using this u substitution as a mechanism to make our problem look easier. How do you choose u? How do you choose this u value? So that's a question I get a lot, and some of the best choices are going to come from picking u if it's in the parentheses or in some absolute value bars or under a radical. When it is in some sort of grouping mechanism, the denominator, it could be in the exponent, we could have some number with some exponent up there. If it's in parentheses, raised to a power. So I'm going to pause and type that out. So, you're not always going to pick the best choice for you on your first try. And sometimes there are multiple choices for you. If your first substitution fails, try a different substitution. All right, but these are just choices, guidelines for how to pick u. So again, we're looking, if we have some expression and there's something in the denominator, or we have some number with an expression in the exponent, in the argument of sine of something, or the log of something. If we have it in parentheses, raised to a power, whatever's in those parentheses might be chosen as u. Or in absolute value bars, if we've got absolute value bars and there's something in between them, or a radicand with something underneath it. Those pieces, those might be what I would choose to make my u value. So let's look at an example. So here we're going to find the value of the integral. The integral is x cubed plus x, that quantity raised to the fifth, times the quantity 3x squared plus 1, integrated with respect to x. So considering my rules from our first slide, right here, x cubed plus x, that is in parentheses raised to a power. All right, and so what I'm going to do here is I'm going to let that piece, I'm going to let x cubed plus x, that is going to be equal to my u value. I prefer to have u on the left side. So we're going to let u equal x cubed plus x. Well, now I can differentiate this. And the derivative of u with respect to x is 3x squared plus 1. And hopefully you notice that once I take that derivative, that piece is also part of my integrand. So if I rearrange this just a little bit, I can say, well, du equals 3x squared plus 1 times dx. So I'll take that dx, we'll call it a differential, and I multiply it up. I'm treating it just like a variable. So now 3x squared plus 1 dx, that represents du. And x cubed plus x represents u. So if I substitute based off of these rules that I've created, I can then say, well, this is u to the 5th, and 3x squared plus 1 dx is now equal to du. So pause, make sure you understand how I made that substitution work. One thing you want to remember when you're substituting is that everything needs to match up exactly right. This is a little puzzle that we are solving. All right? So there may be more manipulation than just multiplying that dx over. Right? So here, that dx, I had to multiply it up to get it on the right side of the equation. So all my x's were together and my u's are alone. But sometimes we may have a number on the right side that moves to the left, and we'll look at more examples with that. All right, so now that we understand how I created that substitution, we can integrate this. And this is very easy to integrate using my power rule. This becomes u to the 6th over 6 plus c. And there you have it. I found the value of my integral. Super easy. I basically just used my power rule to integrate. So we've solved this problem, but we still have our variables in the problem in terms of u. And what we need are variables in terms of x. So I ask you, what did we identify u to be? And if we scroll up, remember u was x cubed plus x. So this is the same as writing x cubed plus x, all of that raised to the 6th, divided by 6 plus c, or rather 1/6 x cubed plus x to the 6 plus c. That's the value of my indefinite integral. So let's do another example. For our second example in this video, we're going to evaluate another integral, again using the substitution method. So we're going to integrate 1 over the square root of 5s plus 4 ds. Now, according to my rules to choose u, I have both a denominator and both something else under the radical. I have an expression under my radical called a radicand. So how do I choose u in this situation? Well, one thing we always do is we try to use algebra if we can to simplify an expression. And a square root can be turned into a 1/2 power. So I'm going to write 5s plus 4. When it was in the denominator, it was positive 1/2. So now I have negative 1/2 ds. So this, once I have it in this form, it's much easier for me to determine how to choose u. In this situation, I'm going to say let u equal 5s plus 4. So u is that expression in parentheses raised to the power. So if we differentiate, the derivative of u with respect to s would equal 5. So normally we're always going to take that differential under the du, and I'll rewrite it. That is du equals 5 ds. So let's look at creating our substitution, because we can't directly substitute everything right now. Inside my parentheses, I said that's going to be my u value raised to the negative 1/2. What I have left is just a ds, and that is not exactly what I have written down here. So can I rearrange what I'm looking at? And in this case, I can divide by 5 on both sides. And if I do that, I have 1/5 du equals ds. So now I have a direct substitution for ds. I can write times 1/5 du. So what this integral now looks like, I can pull that 1/5 in front, multiplying by a constant, is the integral of u to the negative 1/2 du. At this point, I'll use my power rule of integration. The 1/5 stays in front. And I have u to the negative 1/2. So by power rule, that would be u to the positive 1/2 divided by 1/2 plus c. So simplifying this just a little bit, dividing by 1/2 is the same as multiplying by 2. I have 2/5 u to the 1/2 plus c. And, if we have multiple terms in here, we need to distribute that 1/5 to any of those terms. However, the only other term we have in this situation is c. And c is merely an arbitrary constant. It's some constant that we don't know the value of. So 1/5 of that value is still an arbitrary constant. So in general, we do not need to distribute that coefficient to c. We're just going to call it c, some arbitrary constant. So my answer here, I don't want to leave it in terms of u. I need to plug whatever my u value was back in. That is 2/5. U is 5s plus 4 to the 1/2 power plus c. And that's my final answer here, but I just want to tidy it up, make sure it looks the same or in the same fashion as what was presented. So since we started the problem, we had a square root, not a rational power. I'm going to rewrite this as 2/5 times the square root of 5s plus 4 plus c. And that is how you do U substitution.